So this is the API for interior. We're going to define the interior of a subset of a topological space, and then we're going to prove a whole bunch of kind of cute facts about it. So here's the definition of interior. So Lean has interior already, so I've called it interior primed. So what are we starting with here? So X is a topological space, and S is a subset of X. So the interior primed of S, it's a subset of X, and it's defined to be by the union of the U's which are open and are subsets of S. Take the union of those U's. And so unsurprisingly, by definition, or essentially by definition, X is in the interior of S if and only if there exists a subset of X which is open and contained in S such that X is in that subset, because that's the definition of this infinite union. You see, I've used set.membunion if, but then it turned out that these two, I was hoping that would be REFL, but everything is somewhere slightly different order. So I use finish to finish this off. So mem interior primed is the useful fact we have. We can work out, that's an equivalent statement for X being in the interior. So now let's go. So I've got to prove that the interior of S is open. And so however am I going to do that? I guess it's an infinite union of opens, and an arbitrary union of opens is open. It's a bounded union, so I'm going to apply is open bounded union there. And now we're going to see, now this should be easy because everything is obviously open. So intros intros U, and now we've got this hypothesis here. This says U is open and U is a subset of S. So I could do rintros, and then I could do HU and then H there, and now I need to prove that U is open, but HU says that U is open, so this is exact HU. So that's done that one. It's 3 lines long. Now interior subset, the interior of S is a subset of S. So how do I prove that? I need to prove that so intro X, right? Intro X and HX, intros. And now HX says that X is in the interior, so we've got that, right? We've got rewrite mem interior primed at HX. And now we've got something we can use here, so now we can take this apart. So our case is HX with UHU. See what we've got here. Unknown identifier. What have I done? Oh, H little x. With U and HU. So that's HU, comma, and then H. And now H says there exists. So we can keep going. There exists a proof. So this is HUS, comma, H. There we go. And now, so now we've got U is in S and X is in U, and we need to prove that X is in S. Remember, U is a subset of S, that's a function, right? It eats a proof that X is in U and spits out a proof that X is in S. So this is exact HUS, HU. Oh, no, it isn't. HH. It's exactly that. So there we go, 4 lines for that one. Now subset interior, what does this say? If U is open and U is a subset of S, then using the interior of S. Okay, so why don't I do intros XHX, and now rewrite mem interior primed, missed, mem interior primed, and now, so I've got to come up with a U and a proof that it's open. So I've got a U and I've got the proof that U is open. And I need that U is in S, and I've got one of those, and I need to prove that X is in U, and I've got one of those as well. So this is exact U, HU, HUS, comma, what was it again? HX, I think. There we go, and that's 3 lines. See, all these proofs are really short. If you do them all in the right order, they're really nice and short. Interior mono. The interior is a mono. It's it preserves less than or equals to. If S is less than or equal to T, then interior S is less than or equal to interior T. So intros X HX. And then rewrite mem interior or primed at everywhere. And now I want to take HX apart, presumably. Our case is HX with UHU. I did one of those earlier. UHU, I'm just copying from right at the top there. HUS, comma H, and that was HX, I think we should call it. HXU, that would be a good name for it. And now what have we got to prove? And now refine, I've got to come up with a subset of X which is open. So it's obviously going to be U and HU again. And now I need a proof that U is in T. And then I need to prove that X is in U, and that's HXU. So there we go. And now I've got to prove that U is a subset of T. But U is a subset of S, and S is a subset of T. So that is, I guess that's, we could do it like this: exact set dot subset dot trans, or was it? There we go. S set dot subset dot trans H U S H S T. Missed HST. Now that's worked, but in fact we could just put that in there, right? And we could use dot. We could use dot notation. HUS has got type set dot subset, so we could put HUS dot trans HST there. And furthermore, we could just take that term, for it is a term, and dump it there. There we go, and then change that to exact. There we go, another 4-line proof. Interior. The interior of the interior of S is the interior of S. I could have proved that the interior was open. Did I do that? Oh, good, I proved it's open. That would be handy. So this one, I don't directly know how to prove the equality, but I'm going to prove inclusions in both directions. So let's apply set.subset.antisim there. And now I've got to prove both inclusions. And this first one is really easy because it's following from it follows from interior mono, right? This is exact interior mono something. And the something is, it wants a proof. Where's the proof? There. It wants a proof that the interior of S is a subset of S. And I think we did that. There we go. It's interior primed subset. Interior primed subset. Interior primed subset wants an explicit input of S. So that's done that one. And now what's this one? The interior of S. Oh, this looks tricky. Is in the interior of S. Interior mono's no use. Look at this. What about this? Subset interior primed is going to do it, right? It's exactly. You see, it's all about it's all about proving the lemmas in the right order. There we go. That's done it. Except we still have a missing proof. We need to prove the interior is open. Have I done that? Yes. Interior primed open. Interior primed open S. And now we have to prove the interior of S is a subset of the interior of S. And that is got a name. It's probably called set.subset refl or something. No? That's a shame. It's definitely in there somewhere. Hang on. By library search. Oh, there we go. Apparently it's called ruffle.subset. What's going on there? I don't quite understand that. So someone's done something very clever there. I'm sure it used to be called set.subset refl. Ruffle has got type ek. Have they defined ek.subset? Check ek.subset. Yeah, that's a very clever trick. So there you go. Ek dot subset, and then it eats refl, which is the first term of that. That's great. Yeah, dot notation is a very powerful thing. So there you go, and all the proofs were 3 or 4 lines long. Isn't that really neat? And but this very last one here, do you see we used pretty much we used mono, and we used it subset interior, we used interior subset. We used all 4 of them. So there you go. Interior empty. Okay, let's. So these are now somehow examples of interiors. I want to simplify that because y is in the empty set. There we go. Look, we've got to prove that y is not in the interior of the empty set. So I don't know, intro H, that says y is in the interior of the empty set. And so we can deduce then that y is an element of the empty set, right? Because the interior there, you see, what happens, maybe we can just apply, well, this, I wonder if we can do this. In fact, could we have done it here? Could we apply this? Yeah, because interior prime subset, if you apply it to the empty set, it says the interior of the empty set is a subset of the empty set. And so it says for all x, if x is in the interior of the empty set, then x is in the empty set. But x is in the empty set is definitionally what a false. And x is in the interior of the empty set implies false, is definitionally x is not in the interior of the empty set. So in fact it's the exact interior subset empty set. This one. There's a, oh curses, what have I done? Oh, and then I y or something. Oh, I've been too clever. Now I'm fascinated. Actually, I don't want this video to go on too long. So apply works fine. Yeah, it's an exercise. Work out exactly what to feed interior prime subset. Oh, I know what it is. I've got it. It's going to be exact at interior prime subset something. Now let's get this. I just need to say that. Oh man, it needs x topological space, crunch, and then empty set, and then got it. There we go. Yeah, okay. Oh, now we probably don't. Now do we need the simp? I wonder if we can do simp interior primed subset. Oh no, that doesn't do it. Simp at interior primed subset. Has it done it yet? No, empty set. Has it done it yet? It can't do it. Okay. What's the simp do? Why do I need the simp anyway? Oh yeah, to get rid of the if and only if. Anyway, alright. It's done. I'll stop fiddling. Oh, I want to do the same thing here. X to y simp. I've got to prove that y is in the interior of the univ. Aha. So I claim that that's true because univ is open. How am I going to prove that? I'm going to rewrite, I think I'm going to do mem interior. I'm going to prove that there exists a U which is open and it's a subset of univ. Okay, so then I can use univ again. Set dot. I have an open set. Use set dot univ. I guess I could refine this. Refine set dot univ, comma something, and that something is another exists. So I need a proof that it's. Oh, I need to know the proof. That's going to be called set dot univ open or something. Comma underscore. Oh, it's not open univ. It's going to be called one or the other. Ah, what? Why is univ open? What's going on here? Check open univ. Ah, is open univ. Hard luck. There we go. And now what have I got to prove here? I've got to prove. I'm going to prove that so that's ruffle. We just learned that one, ruffle.subset, and then underscore. And now I've got to prove that y is in set.univ, and that's true. That's by triv. There we go. So that's done that one. So I had to, you see, I was sort of in term mode here, so I had to pop back into tactic mode with by. And now the interior of the intersection is the intersection of the interiors, and I think again I need to apply that set.subset there. I think this is the way to start. I'll prove the inclusions in both directions. And now for this first one, check out my snippets. For this first one, to prove a subset, I mean, apply set.subset inter. That will be a thing, right? Yeah. So I could refine it. Refine set.subset inter underscore underscore. And now I've got to prove, and both of these are, that's interior primed mono something, and this is also interior primed mono mono something, and now these are both by what's this because this will be called inter subset left or something. I better put it in brackets, inter subset left. Oh, it's called set.intersubset left, and it wants the sets. So there we go. And now this will be set.intersubset right, and it's S and T. So that's one half, and the other half, I don't know how to do it other than by, I think we need to do rintro, rintro x, and then hxs, hxt, because I'm being in an intersection is two things, and then rewrite set, what's this called? Mem interior primed at everywhere, and now take everything apart. Our case is hxs with uhu. It's hus, comma hx or something. Yeah, hxu. And then I want to take hxt apart with it, and that's going to be a v and an hv, an hvt, and hxv there. And so now finally I've got x is in u and v are both open, u's a subset of s, v's a subset of t, and I need to come up with an open set which is contained in s intersect t such that x is in it, and it's the intersection. So this is refine u intersect v, comma something. So now I've got to prove that u intersect v is, so u is open and v is open. So what will that be called? That will be called is open inter with a small I. Is it inter? That's annoying. It's not called is open inter. Is open dot inter. Ah, bingo. Is open dot inter. Why do I call that? Is open dot inter. Oh, I see why. It's because I can do h. It's because I can do hu dot inter hv, right? And now I've got to prove that u intersect v is a subset of s intersect t. Oh, that was on an earlier sheet. So u's in s and v's in t. So this is inter subset inter or something. Set dot inter subset inter. That was it. Comma underscore. Ah. Didn't like inter subset inter. What's the error? Oh, it wants the. Oh, of course, it wants the proofs. HUS HVT. I can supply those proofs for you. And now we've got to prove that x is in u intersect v, and that's an and statement. That just says x is in u and x is in v. So that's hxu hxv. There we go. And that's the end of everything. Thank you very much for watching. By the way, did you notice that the end of my last video, not this one, the one before, I said that's the end of everything, but there was an error. And in fact, it's a bug in a tactic, so that's kind of cool.